Okay, so when we last left off, we were discussing orbital shells and subshells. And now that we have an idea about the different orbital shells and subshells, we're going to try to answer the question, how are shells and subshells sorted by energy? So first and foremost, if we think about shells, which are denoted by values of n, in other words, the different rows in the periodic table, for different n values, the lowest n corresponds to the lowest energy shell, and by extension, the orbitals in that shell would be lower in energy. As we have an increasing n value, we have an increasing orbital energy. So for example, your 1s, which is n equals 1, that orbital is lower in energy than the 2s orbital, which is n is equal to 2, which is lower in energy than the 3s orbital, which is n is equal to 3. As we increase our n value, as we increase our shell number, our energy increases. Now, let's think a little bit about how are subshells sorted. How are subshells sorted in terms of increasing energy? Well, thinking about subshells, which are regions of a row in the periodic table, which are denoted by an L value, for the same n value, s orbitals, which is L equals 0, are lower in energy than p orbitals, which is L equals 1, which is lower in energy than the d orbitals, which is L equals 2, which is lower in energy than the f orbitals, which is L equals 3. So for the same n value, as L increases, our orbital energy increases. So for example, our 2s, or well, let me use another example. So for our 3s orbital, it's lower in energy than our 3p orbital, which is in turn lower in energy than our 3d orbitals. Increasing L, increasing subshell number, increasing energy. So we can take these two ideas of how orbitals are arranged in terms of increasing energy and generate an orbital energy diagram, which arranges the orbitals from the lowest energy all the way to the highest energy. And we're going to be using these orbital diagrams extensively to describe different atoms and ions. So you're responsible for being familiar with this orbital energy diagram and how orbitals are arranged in order of increasing energy. So to help you become more familiar with this idea and these orbital energy diagrams, we're going to talk a little bit about how these orbital energy diagrams function in practice. So an orbital diagram specifies each orbital arranged in order of increasing energy. Electrons in each orbital are represented by an up arrow or a down arrow. And as we recall from last class session, we can fit a total of 2 electrons per orbital. Orbital box diagrams follow a very similar scheme where we write each orbital as a box that can hold 2 electrons. And these orbital diagrams arrange orbitals vertically in order of increasing energy. So, one of the terms that you'll see often in orbital box diagrams is this idea of degenerate orbitals. Now, what does this mean? Well, these are orbitals with the same n and L value that have the same energy. So for example, all of these 3p orbitals have the same energy. And the reason why it's important to know this is that Because these orbitals have the same energy, they're filled with equal preference. You can place an electron in any of these orbitals with equal preference. Now, to make sure we're all paying attention, and that we're familiar with the relative orbital energies, I'd like you to rank the following orbitals in order of lowest to highest energy. So we have our 2s, 3s, 3px, 3py, and 3d orbitals. And I'd like you to take these orbitals and I'd like you to rank them in order of increasing energy. And remember, our shortcut from our orbital energy diagram looks something like this. 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p. So this is our ranking of our different orbitals in order of increasing energy. So I'd like you to take about 3 to 4 minutes and I'd like you to rank the following orbitals in order of increasing energy. And don't be shy to share your responses in the chat or verbally, or ask a question in the chat or verbally. And we're already starting to see a few responses in the chat. Wonderful. Let's try to get a few more responses and then we'll discuss in about another 2 to 3 minutes. And if you're unsure about your response, don't be shy to ask a question in the chat. That's equally valuable to advance our discussion. So we'll discuss this example in about another minute to a minute and a half. Let's try to get a few more responses in the chat or even some questions. The main trick for these problems is just to remember the relative energy of each of these orbitals. Okay, so let's discuss this example. So first we sort in order of n. So our 2s is lower in energy than our 3s, 3px, 3py, and 3d orbitals. Now, once we have this sorted, we then sort in order of L. So our 2s orbital is the lowest in energy. Next, we look at L values. So 3s is L equals 0. These 3p orbitals are both L equals 1, and the 3d is L equals 2. So now we sort in order of increasing L. Note, the 3px and 3py, don't worry about these x and y terms. So if we think about what the 3px and 3py are representing, we're just trying to describe two different 3p orbitals. But fundamentally, are these orbitals still both 3p orbitals? Do these orbitals have the same energy? Do these 3p orbitals have the same n and L value? Do they have the same number and letter describing that orbital? Yes. So as a result, these 3p orbitals, the 3px and the 3py orbital, are the same in energy. Finally, the 3d orbital is the highest in energy. Does this ranking make sense to everyone? You're going to want to be familiar with the relative energy of each of the orbitals. Because what we're going to do is, from this relative ranking of orbital energy, we're going to begin to fill in these orbital diagrams. Any questions on these examples? If not, let's keep going. And let's talk about how to draw orbital box diagrams. So first things first, atoms have electrons, and we can figure out the number of electrons by taking the atomic number minus the charge. So for example, if we were looking at just magnesium alone, neutral magnesium, what would magnesium's atomic number be? What would magnesium's atomic number be if we're looking at the periodic table? What would magnesium's atomic number be if we're looking at the periodic table? 12, okay. So neutral magnesium, our number of electrons, would be equal to 12 minus 0, which is equal to 12. So we know how to calculate the number of electrons. Now that we have our number of electrons, we place our electrons in orbitals from the lowest to the highest energy orbital until all electrons have been placed. Now, there's an orbital energy order that you're going to have to memorize. And I always like to rewrite things to help me remember it. It's 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p. So this is the orbital energy order that you'll need to be familiar with for this class. And this covers and will allow you to write orbital box diagrams for the majority of elements in the periodic table. So let's do an example. So for beryllium, if I look up beryllium in the periodic table, how many electrons does beryllium have? What is beryllium's atomic number? 4, yep, exactly right. So we have 4 electrons in beryllium. Now we're going to draw out our basic orbital box diagram. So we have our 1s orbital, our 2s orbital, and then remember, for our 2p orbitals, we have 3 of them. Now that we have our orbitals arranged in order of increasing energy, we're going to take these 4 electrons and we're going to fill in this diagram. So each arrow represents 1 electron, each box represents an orbital, and we can add 2 electrons per orbital. So I placed my first 2 electrons, and now I've filled my 1s orbital. So what's the next orbital that I have to fill? What's the next highest energy orbital?
2s.
Yep, exactly right. And I fill it with 2 electrons. I've used up all 4 of my electrons, and this is a complete orbital box diagram. Now what's really cool from here is that we can note the number of electrons in a given orbital n and L value to write out electron configurations. So we note in our 1s orbital, how many electrons do we have? How many arrows do we see in our 1s orbital? 2. Exactly right, exactly right. So we put the number of electrons as a superscript because we have 2 electrons. Likewise, in our 2s orbital, how many electrons do we have? 2. So we put a 2. So this would be a complete electron configuration. Which indicates the number of electrons in each degenerate set of orbitals arranged in order of increasing energy. So to unpack electron configurations a little bit, electron configurations list the subshells N and L values that contain electrons and indicate the number of electrons in that subshell with a superscript. So for example, if we're looking at carbon, so let's do our electron count. So for carbon, if we look up carbon in the periodic table, what is carbon's atomic number? 6. Okay, so now let's write out our orbitals. So we have the 1s orbital, the 2s orbital, and the 2p orbital. We take our 6 electrons and we add 2 electrons to our lowest energy 1s orbital. Are we done? Have we used up all 6 of our electrons? Have we drawn a total of 6 arrows?
Professor, I have a question really quick.
Yes.
When you're what you're writing in the 1s, what is that?
That is the orbital N and L value. So remember our general orbital energy ranking that went 1s, 2s, 2p, 3s, 3p?
Yes.
Yes. So we're arranging our orbitals in order of increasing energy, remembering that the s orbital, the s subshell has 1 orbital, while the p subshell has 3. And I'm just labeling the orbital shell and subshell, so that way I know when I'm writing my electron configuration which orbital I need to write out. Does that make sense?
Yeah, but what is it that you're writing? What is the writing on the inside the box?
So
Is it 7L?
So each arrow, so an up arrow or a down arrow represents 1 electron. And in each orbital, we can hold a total of 2 electrons per orbital.
Okay, got it.
So these arrows are indicating electrons that we're filling into this orbital diagram from our total of 6 electrons, which we got from the atomic number. And we fill this diagram from lowest to highest energy until we've completely used up our electrons. Does that make sense?
So that's an upper and lower arrow.
Yep, exactly right.
Okay, thank you.
Mm-hmm. So now that we've used 2 electrons, what's the next orbital that we fill? What's the next highest energy orbital? The 2s, yep. So we add 2 electrons, an up arrow and a down arrow, an up spin and down spin electron to our 2s orbital. And now we still have 2 electrons to go. So now we're gonna fill our 2p orbitals. And as a general rule, you fill your empty degenerate orbitals first. So based on that, we put 1 electron in one of our 2p orbitals, and we put our second electron in our empty 2p orbital. We'll talk more about this rule in a moment. In terms of the electron configuration, let's do some counting. So in our 1s orbital, how many total electrons do we have in all of our 1s orbitals? How many electrons do we see? In our 1s orbital, we see 2 electrons. Now let's look at our next highest energy orbital, the 2s orbital. How many electrons do we have? How many electrons do we have in the 2s orbital? 2, exactly right. Let's keep going now. Now for our 2p orbital, and this is important, looking at all of our 2p orbitals, what is the total number of electrons that we see? How many total electrons do we see?
2.
2. Yep. So let me fill that in using the appropriate color. Yep. Perfect. So now we have a complete electron configuration for carbon. Does this make a little bit more sense so far? Is everyone feeling a little more comfortable with this idea of writing electron configurations?
Professor,
Yes, how can I help?
why 2p each orbital is not hold 2 electrons, like the 1s, 2s?
So the reason for that, and we'll talk about it a little bit in a moment, is that pairing electrons, having 2 electrons in an orbital, costs energy. So if there is a degenerate orbital, if there's another orbital that's empty, that has the same energy, it's preferred to place an electron in the empty orbital of the same energy first.
Okay, thank you.
Mm-hmm. And to elaborate on that, let's unpack these electron configurations a little bit. So we know that we fill our orbitals from the lowest to highest energy. We denote the number of electrons in each orbital with a superscript. So for example, for hydrogen, we'd have our 1s orbital with 1 electron. So in our electron configuration, we'd note that we have a 1s orbital with 1 electron. Okay? We're familiar with this idea from our earlier examples on electron configurations. Now, the beautiful thing about electron configurations is you don't actually have to write a full orbital box diagram. You can actually read from the periodic table, and from the periodic table, you can write out reasonable electron configurations. The periodic table is divided into regions of 2, 6, 10, and 14 columns, corresponding to our S, P, and D, and F blocks. We place electrons in orbitals from the lowest to highest energy orbital until all electrons are placed. So we have this general filling order. And the nice thing about the periodic table is that each box in the periodic table represents room for a single electron. And each step to the right on the periodic table adds an electron to the lowest energy orbital. So for example, if we moved 1 step to the right on the periodic table, we'd add 1 electron. Further, and this is pretty cool, each of these sets of columns in the periodic table represent a unique block. And depending on where you are in the periodic table in terms of the row and the column, it tells you the orbital n and L value that you are filling as you move across the periodic table. So it's really, I would really focus on this picture, as this picture in terms of labeled shells and subshells in the periodic table would be really useful to know, because it allows you to use the periodic table that you're provided on all of the exams to write electron configurations. So a little bit more on this. So each row represents a shell. So for example, n equals 1, n equals 2. each region of the periodic table represents a subshell, S, P, D, F. Let's show how this works in practice. Let's show how this works in practice. So if we're trying to write out the electron configuration for helium, if I look up the periodic table, for a moment, I see that helium is in the first row of the periodic table, and it is in the S block. So I write out my 1s orbital, and now all I have to do is count the number of spaces. So I have 1, 2 spaces in the S block. So I have 2 electrons in my 1s orbital. To do this the more traditional way, as students may prefer that, if we look up helium in the periodic table, how many electrons does helium have? How many electrons does helium? 2, exactly. So we have 2 electrons to work with. So we write out our empty orbital box diagram. So we have our 1s and 2s orbitals. We take our 2 electrons and we fill our orbitals from lowest to highest energy. So our 1s gets filled first. So then, now that we've used up all of our electrons, how many electrons do we have in our 1s orbital? What is our complete electron configuration for helium? 2. Yep. So it would be 1s2. Exactly right. So these are 2 methods. One directly uses the periodic table. The other, you draw an orbital box diagram and then you interpret that orbital box diagram. Both methods are valid. Both methods are perfectly fine and will get you to the right answer. I'm just showing you as many methods as possible, and you can pick the one that you're comfortable with.
Professor,
Yes.
for page, I'm sorry, my computer skipped out or froze. Can you go over page 60? You were talking about magnesium and then something about number of electrons and then 12 minus 12.
Yeah, so the number of electrons is the atomic number minus the charge. So for neutral magnesium, we can figure out the number of electrons by finding the atomic number, which is 12 in the periodic table, and subtracting the charge, which in this case is 0. So this is how you can count electrons from the periodic table given an element's symbol and the charge, just like what we did for isotope notation.
Oh, yes, yes. Okay, thank you.
Perfect, perfect. So I'm going to show another example, this time for boron, and we're going to showcase how both methods can function. So let's draw out our sample periodic table. So let's draw out our sample periodic table. And let's try to write out the configuration for boron. So if you look at the periodic table and you try to find boron in the periodic table, boron would show up right here with an atomic number of 5. Now, based on the location of boron in the periodic table, we can use the periodic table method to write a configuration for boron. So let me label each of these blocks. So we have an S block and the P block. And what we're going to do is we're going to start from the top of the periodic table and work our way down. So initially, we start out in our 1s block. We start out in the first row of the periodic table in the S block. Now, when we traverse the periodic table to reach boron, we move across the periodic table from left to right. As you see, we have 1, 2 spaces in the first S block, so we filled it with 2 electrons. Continuing on, we're going to fill our next highest energy shell and subshell, which would be the 2s subshell. 2s, second row, S block. In turn, we move across the periodic table. We haven't yet reached boron, so we move 2 spaces in our 2s block, so we have 2 electrons. Finally, we've moved into the 2p block, and to reach boron, we need to move 1 space into the 2p block, so we have 1 electron in our 2p orbitals, sorry. So this would be the complete electron configuration for boron using the periodic table method. Does this make sense to everyone? This is a more direct method of reading the periodic table and writing out electron configurations. If you don't like this method, you don't have to use it. There are plenty of other methods at your disposal. So let's show the traditional method. So boron with its 5 electrons, we can just as easily draw out a traditional orbital box diagram, fill in that diagram, and count the number of electrons. There's no reason why we can't. So putting together our orbital box diagram for boron, we took our 5 electrons and filled our orbitals from lowest to highest in energy. And as we see, we get the exact same final result for our electron configurations. In our 1s orbital, we have 2 electrons. In our 2s orbital, 2 electrons. In our 2p orbitals, we have 1 electron. So as you can see, both methods yield the same result. Any questions on writing electron configurations using the orbital box diagram method and the periodic table method? Is this making sense to everyone so far? Any questions that I can address before we continue our discussion?
So the second example where we write it out, the one on the bottom, what is that naturally given to us, or?
This is what you'd be, so the orbital box diagram you'd be able to draw just like we did in the earlier examples. And then once you've drawn out and filled in the orbital box diagram, then you simply count the number of electrons in each set of orbitals, each unique shell and subshell.
Okay, thank you.
Does that make sense?
Yes.
Perfect, perfect. So let's keep going now. And I'd like you to work on the following example. I'd like you to write an electron configuration for magnesium, and I'd like you to fill in an orbital diagram. So you can type the electron configuration in the chat, and if you look in Zoom features, in the upper portion, you'll see this black tab titled Meeting Options, and if you go into the drop-down menu, it'll have an option called Annotate. And with the Annotate feature, you can actually draw out your proposed orbital diagram or draw out your proposed electron configuration on the empty space that I provided with this whiteboard. So let's take about 3 to 4 minutes and focus on writing an electron configuration for magnesium and filling in an orbital diagram. If you're able to use the annotate feature to share your proposed orbital diagram, that would be great. If not, you can provide your electron configuration and proposed orbital filling order in the chat or verbally. And if you're unsure about your response, you can also ask a question in the chat or verbally. So I'll give everyone about 3 to 4 minutes, and we already see a student is able and starting to use the annotate feature, so don't be shy. There's plenty of space for multiple students to share their proposed responses. And if not, don't be shy to share your responses in the chat. And we'll discuss this example in about 3 to 4 minutes. The 2p orbitals can hold a maximum of 6 electrons. That's correct, because we have 3 orbitals with 2 electrons each. And don't be shy to share your proposed electron configuration in the chat. And even if your results or your response disagrees with your classmates, don't worry. The more responses we have, the more I can understand the logic associated with the class's problem solving methods, and the more directed feedback I can provide. And if anyone would like to try using the annotate feature, I know it's a new feature in Zoom, but it's really useful, especially for sharing drawn structures. Again, if you notice the small little black tab at the top of your screen on the Zoom view, if you click on that tab, it'll have different meeting options, one of which is called annotate. And if possible, I'd like to see someone attempt to write an annotated electron configuration, or you can share a picture in the chat, or you can unmute your camera and share your proposed picture for the electron configuration and orbital diagram. If not, we'll discuss this example in about another minute. And don't be shy if you have a question to ask your question in the chat or verbally. Okay, so let's discuss. So first things first, magnesium. How many electrons does neutral magnesium have? 12, yep. So magnesium has an atomic number of 12. So our number of electrons is equal to 12 minus 0, which is 12. We have no charge, so we have 12 electrons. Perfect. Now we write out our orbital diagram. So we have 1s, 2s, 2p, 3s. And now we take our 12 electrons and we fill our orbitals from the lowest to the highest energy. So we fill our 1s orbital, we use up 2 electrons, we have 10 remaining. We fill our 2s orbital, we have 8 electrons remaining. We fill each of our 2p orbitals, we have 2 electrons remaining. Finally, we fill our 3s orbital and we've used up all of our electrons. Does this example make sense so far? Now that we've filled our orbital box diagram, we count the number of electrons in each orbital. So in our 1s orbital, we have 2 electrons. In our 2s orbital, we have 2 electrons. How many electrons are in all of our 2p orbitals? How many electrons are in all of our 2p orbitals? 6. Finally, in our 3s orbital, we have 2 electrons. So this gives us the complete electron configuration and orbital box diagram for magnesium. Does this make sense to everyone so far? Any questions on this example? Perfect, perfect. So let's do another example, and I'd like you to write the electron configuration and fill out an orbital diagram for oxygen. And don't be shy to share your responses in the chat or using the annotate feature. So this is a really important skill in terms of counting electrons and writing electron configurations, because we're going to actually use electron configurations to begin to draw and to start to put together and draw out the structures for many molecules. So let's work on this example for about 2 to 3 minutes, and then we'll come together as a group to discuss. And again, don't be shy to share your responses or a question in the chat. And we're already seeing a reasonable pool of responses in the chat, so we'll discuss in about another minute. And if you have any questions at all during the session, don't be shy to ask. Okay, so let's discuss this example. So first, for oxygen, if we look up oxygen in the periodic table, how many electrons do we have? What is oxygen's atomic number? Eight. Yep, exactly right. So we have 8 electrons to work with. We're going to write out our orbital box diagram. One S, 2S, 2P. Okay, now we're going to fill our orbital box diagram from the lowest to highest energy orbital. So we fill our 1s orbital first with 2 electrons. We have 6 electrons remaining. Then we fill our 2s orbital. We have 4 electrons remaining. For our 2p orbital, we fill each of our empty orbitals first, and then we pair our last electron. and that gives us 0 electrons remaining. Now, for our electron configuration, we just count the number of electrons in each orbital. So for the 1s orbital, we have 2 electrons. For the 2s orbital, we have 2 electrons. And for our 2p orbital, we have 4 electrons. And now we have a complete electron configuration for oxygen. Does this make sense to everyone so far? Any questions on this example? If not, let's keep going and let's talk a little bit about orbital diagrams in detail. So Hund's rule states that empty orbitals of the same energy are filled first before pairing electrons. So for example, in the following diagram, which happens to be for nitrogen, notice how our electrons in the 2p orbital are left unpaired. We only pair our electrons if we have no empty orbitals of the same energy remaining. So in general, we fill empty degenerate orbitals first before pairing. So we've done some examples where we looked at the electron configuration for atoms. Let's figure out the electron configuration for an ion. Remembering that the number of electrons is equal to the atomic number minus the charge. So let's look at O2 minus and let's write a valid electron configuration and orbital diagram for O2 minus. And we'll discuss this example in about 2 to 3 minutes. Remember, we're just putting together 2 skills that you've already had developed. You know how to count electrons. You're starting to develop this skill of writing orbital diagrams. Now all you have to do is put those 2 skills together. And don't be shy to share your proposed electron configuration in the chat. And make sure to double check your electron count when writing out your electron configuration. And I see a few reasonable responses in the chat. And just make sure that your electron count is accurate for O2 minus. Let's try to get a few more responses in the chat and then we'll discuss in about another minute and a half. And let's try to get a few more responses in the chat, and we'll discuss in about another 30 seconds to a minute. And don't be shy if you're unsure to ask a question as well. Okay, so let's discuss. So first, we know that oxygen's atomic number is what? Oxygen's atomic number is what?
8.
8, exactly. So then for our number of electrons, we have for O2 minus, we take our atomic number and we subtract the charge. And our charge in this case is -2. So that gives us 10 electrons to work with. Now we write out our orbital box diagram, 1s, 2s, 2p, 3s, and now we fill our orbital box diagram from the lowest to the highest energy. So first things first, we add 2 electrons to our 1s orbital. We are now at 8 electrons. We add 2 electrons to our 2s orbital. We're at 6 electrons. Finally, we completely fill in our 2p orbital. We have 0 electrons remaining. And now that we have that set up, we fill in our orbital. We filled in our orbital box diagram. We now write out our electron configuration. So in our 1s orbital, we have 2 electrons. In our 2s orbital, we have 2 electrons. And in our 2p orbitals, we have 6 electrons. So here we go. We have the complete electron configuration for oxygen 2 minus. Now, and this will be a really key idea. Is everyone comfortable with writing out electron configurations and orbital box diagrams for ions? The only thing that's new is that you have to make sure your electron count is accurate. Does that make sense? Perfect. So now what I want everyone to do, and this may seem a little bit like repetition, I'd like you to write the electron configuration and orbital diagram for neon, which is a noble gas. And I'd like you to tell me, how does that noble gas electron configuration compare to our ion configuration? So let's work on this example for about 2 to 3 minutes, and then we'll discuss. And don't be shy to share your responses in the chat. And even if your response differs from your classmate, the pool of responses can help me provide more directed feedback. And we'll discuss this example in about another 1.5 to 2 minutes. And remember, you can save some work and save some time. If your electron count is the same, your electron configuration will be the same. And we'll discuss this example in about another minute. And if you have a question, don't be shy to ask it in the chat or verbally. Okay, so let's discuss this example. So for neon, neutral neon, what is neon's atomic number? 10, okay. So we have 10 electrons. Does that sound familiar? Is that the same as O2 minus's electron count? Are these two electron counts the same? Yes. So then, by extension, our electron configuration will be the same. Same number of electrons, same electron configuration. So, filling in our orbital box diagram, 2, 4, 6, 8, 10. Okay, so our electron configuration for neon is 1s2, 2s2, 2p6. And as we notice, the configuration for neon is exactly identical to the configuration of O2 minus, which brings to us this very important observation. Ions typically have what's known as a noble gas electron configurations. So as we notice, the electron configuration for an ion, O2 minus, closely matches the electron configuration for our noble gas. Does this make sense? Perfect. This will be an important observation to keep in mind for later. So on that same note, let's take about 2 to 3 minutes and let's try to write an electron configuration for sodium plus and fill in an orbital diagram. Remember, make sure your electron count is correct, and then you'll be more than okay in completing this problem. We'll discuss this example in about another 2 minutes. And you may say, why am I giving so little time? Because if you count your electrons, you'll notice a trick. and we'll discuss in about another minute. Don't be shy to submit your response in the chat or to ask a question. Remember, if we have the same electron count, we'll have the same electron configuration. Okay, so let's discuss. So for sodium plus, so first, if we look up sodium in the periodic table, what is the atomic number? 11, okay. So then our number of electrons is equal to our atomic number minus the charge, which gives us 10 electrons. Same electron count as the previous example, so we should expect the same electron configuration. We write out our orbital box diagram, and then we fill in our orbital box diagram from lowest to highest energy. Now that we've filled in our orbital box diagram for sodium plus, we can write out our configuration, which would be 1s2, 2s2, 2p6. Again, we have an ion with a noble gas configuration. This is an overwhelming trend that we see when we look at the electron configurations for most ions. Does this example make sense? Perfect. Okay, so now let's do something a little bit different. I'd like you to take a moment and let's spend about 3 minutes on this example. I'd like you to write the electron configuration and try to fill in an orbital diagram for silicon. So let's work on this example over the next 3 minutes, and practice really makes perfect for electron configurations. I really want to make sure everyone's comfortable because this is a central topic of the take-home lab assignment that you were given last week. And I want to make sure that everyone can write configurations effectively. So we'll take about 2.5 to 3 minutes on this example. And don't be shy to share your proposed electron configurations in the chat. And I'm starting to see some reasonable responses in the chat. Don't be shy to submit additional responses in the chat, even if it necessarily doesn't agree with your classmates' responses. The more pieces of information you have, and the more student responses I receive, the more feedback I can provide and the more I can tune the examples that I provide in later class sessions. So we'll discuss this example in about another 1.5 minutes, and don't be shy to submit your response. Okay, so we have a nice reasonable pool of responses. So first things first, for silicon, how many electrons do we have? How many electrons do we have?
14.
14. Okay. One thing I also want you to note is that silicon is right below carbon. You'll see why this is important in a moment. So we have 14 electrons to work with. So we're going to generate our orbital box diagram. 1s, 2s, 2p, 3s, 3p. Now we're going to fill our orbital box diagram from the lowest to the highest energy. So we used up 12 electrons so far. For our last 2 electrons, we placed them in separate degenerate orbitals. Writing out our configuration, we'd get 1s2, 2s2, 2p6, 3s2, 3p2. So this is the configuration for silicon. I'd like you to compare that to the configuration for carbon. Notice how the only thing that has really changed in our configuration is we're now in a larger shell. Does everyone see how the configuration for carbon and silicon are very, very, very similar? Does everyone see the similarity between carbon and silicon's configuration? Okay, we'll leave that in the back for now. Just keep that in the back of your mind when we continue this discussion. Any questions on this example? If not, let's keep going and let's look at the electron configuration for sulfur 2- and let's fill in an orbital diagram. Again, practice makes perfect. And many of the examples in these notes can be directly copied onto your lab report. So these have been pretty carefully designed for that fact. So we'll spend about 2 to 3 minutes on this example, and then we'll discuss momentarily. And don't be shy to submit your proposed electron configuration in the chat, or if you have a question, to ask a question in the chat. Or verbally, of course. And don't be shy to submit your response, even if it disagrees with a classmate. The more responses we have, the more feedback I can provide, and the more readily you can revise your logic once you've seen the solution or verify the steps in your problem-solving process. And we'll discuss this example in about another minute. Okay, so let's discuss. Again, we have to be a little bit careful here. For sulfur 2-, what is sulfur's atomic number in the periodic table? What is sulfur's atomic number? 16, okay? So for sulfur 2-, our number of electrons is equal to our atomic number minus the charge, which is 18 electrons. Now we write out our orbital box diagram. And we fill our orbital box diagram from the lowest to the highest energy. 2, 4, 6, 8, 10, 12, 14, 16, 18. And that gives us an electron configuration of 1s2, 2s2, 2p6, 3s2, 3p6. Any questions on this example? Any questions on this example? Does this make sense so far? Perfect. So let's look at another example and let's write the electron configuration and orbital diagram for calcium. Let's spend about another 2 to 3 minutes on this example and then we'll discuss. And don't be shy to share your responses in the chat, ask questions in the chat, or ask questions verbally as well. And we're already starting to see a few responses in the chat. Don't be shy to submit your responses and we'll discuss in about 1.5 to 2 minutes. Sure, I can scroll up for the last question. And we'll discuss the example for calcium's configuration momentarily. Okay, so let's look at calcium. Let's look at calcium and let's try to write an electron configuration. So for calcium, what is calcium's atomic number? How many electrons does calcium have?
20.
20, yep. Okay, so we have 20 electrons to work with. So now let's write out our blank orbital box diagram. And you notice that after drawing the orbital box diagram so many times, you almost have it memorized, right? I find the best way to become familiar with orbital box diagrams and electron configurations is just to practice a bunch of examples. So for 20 electrons, we take our electrons and distribute it from the lowest to the highest energy orbitals. So we've used up all 20 of our electrons. And now writing our configuration, we'd have 1s2, 2s2, 2p6, 3s2, 3p6, and this is the part where students sometimes get confused. It's 4s2. So after the 3p orbital, the next highest energy orbital is the 4s. So here's our complete electron configuration for calcium.
Professor, how come we don't go to, I thought it was 3D.
Yeah, so this is a quirk associated with the relative orbital energy, in that the 4s orbital is actually lower in energy than the 3d orbital. The explanation related to this is covered in general in the higher level general chemistry sequences, but essentially the 3D orbitals are their shape and how the electrons are distributed makes it so the 3D orbital electrons are less stabilized by the nucleus compared to a 4s orbital electron. And this is just one thing, this is one quirk that you'll have to remember and be familiar with, as it pops up a lot for elements in the 4th and 5th row of the periodic table. Does that make sense? Did that address your question? Perfect. So let's keep going now, and let's try to write an electron configuration for bromine and fill in an orbital diagram. So this will emphasize this point. And remember your general orbital filling order. Bromine has a fair number of electrons, so this will take you a little bit of time. And we'll discuss this example in about 3 minutes, just to give you enough time to fill in your complete orbital diagram, since bromine has about a fair number of electrons. And don't be shy to share your responses in the chat, and I'd be happy to provide feedback. And remember the d orbital, the d subshell, holds 10 electrons. It can hold up to 10 electrons. And just make sure that your electron count is correct, and you should be more than okay in this problem. And don't be shy to submit your response, even if it disagrees with your classmates. And if you have any questions I can address, don't be shy to ask in the chat or verbally. And let's try to get a few more responses in the chat, and then we'll discuss. That makes sense. That makes sense. And we'll discuss this example in about another minute to a minute and a half. So let's discuss this example. So for bromine, what is bromine's atomic number? What is bromine's atomic number? 35, 35. Okay. So with that in mind, we have 35 electrons to work with. So let's write out our orbital box diagram. And I really like this bromine example because it hits all the major points that you need to be familiar with, moving into more complicated electron configurations. Remember, after the 3p comes the 4s orbitals, followed by the 3d orbitals. And for the 3d orbitals, remember, there are 5 of them. Okay, so now that we have this diagram set up, we fill in with our electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 35. Well, it's a little bit tiring to write that out. So then our configuration will be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p5. Okay, perfect. Does this example make sense to everyone? Does this example make sense? Perfect. So let's do another example. We already did calcium, so let's make a change up here and let's look at the electron configuration for phosphorus. So I'd like you to write out the electron configuration for phosphorus and fill in an orbital energy diagram. And we'll discuss this example in about another 2 to 2.5 minutes. And again, don't be shy to share your electron configurations in the chat. Throughout this process, we're essentially going over examples that cover a large portion of electron configurations you have to write in this class. And the responses I'm seeing in the chat look great. So now let's discuss. So for phosphorus, what is the atomic number for phosphorus? 15. Okay, perfect. So now we have 15 electrons to work with. So let's write out our orbital box diagram. So we have 1s, 2s, 2p, 3s, and 3p. And now we fill our orbital box diagram from lowest to highest energy. 2, 4, 6, 8, 10, 12, 13, 14, 15. Remember, you fill empty orbitals of the same energy first. That in turn leads to a configuration of 1s2, 2s2, 2p3, 2p6. I'm getting ahead of myself here. 3s2, and then 3p3. So this is the configuration for phosphorus. Any questions on this example?
For 3P, I was wondering why it only has one for each box.
So in general, rather than placing our 3 electrons with one paired and one empty orbital, one rule in electron configurations is that you fill empty orbitals of the same energy first. So that's why we have 1 electron in each of these 3p orbitals rather than 2 and 1. Does that make sense? Did that address your question? Perfect. Any
Professor,
other?
before
Yeah.
we move on, can you scroll up real quick to the example beforehand?
Mhm.
I'm just trying to see how the diagram lays out.
Yeah, no problem at all.
Okay, thank you.
Perfect, perfect. Okay, now many of you likely are getting tired of writing out every single part of these electron configurations, and there's actually a trick. We can abbreviate electron configurations by sorting electrons into inner shell electrons or core electrons and outer shell electrons or valence electrons. So we can abbreviate the core electrons using the configuration of the closest noble gas filled before your element. So let's also define some further terms. Valence electrons are electrons in the outermost energy level, the electrons in the orbitals with the largest N value. And the number of valence electrons equals the group number for main group elements. And really key to note here, D and F orbital electrons are not valence electrons. So for example, lithium, it's a group 1A element. So we'd have one valence electron, where the valence electrons in this case are the electrons in our 2s orbital, because it's the outermost orbital. Now, the preceding noble gas is helium. So if we look at our periodic table, we'd have helium before lithium. So we use the configuration of helium to abbreviate our inner shell or core electrons. So we'd rewrite our configuration for lithium from 1s2 2s1 into helium 2s1. This makes it really clear which electrons are inner shell and which electrons are valence electrons. And these valence electrons are really important. Does this idea make sense to everyone? For example, for fluorine, the electrons that are in the orbitals with the largest n value are the electrons in our 2s and 2p orbitals. And as we can see, we have 7 valence electrons, which matches our group number. We can abbreviate our inner shell, we can abbreviate our core electrons using the configuration for helium. And that gives us the following abbreviated configuration for fluorine. Does this make sense to everyone? You find the closest preceding, the closest noble gas before your element, and you abbreviate your inner shell or core electrons using that noble gas configuration.
Will it always be noble gas?
Yes, abbreviated configurations always use the preceding noble gas. So let's do an example. So we have 3 cases here. I'll do the first one. So in this case, we're looking at oxygen. So if we look at the periodic table, we have helium, and then we have the rest of our row, and then we have oxygen. Okay, so oxygen has a total of 8 electrons to its name. So its long form configuration would be 1s2, 2s2, 2p4. Okay, we can abbreviate these inner shell electrons as our closest preceding noble gas, which is helium. So we'd write our abbreviated configuration as helium 2s2, 2p4. Does that make sense to everyone? Is everyone comfortable with this idea? So let's keep going now, and I'd like you to take about 3 to 4 minutes, and I'd like you to try to write the abbreviated configuration for boron and beryllium. And note, just as a way to check your work, your number of valence electrons will always match your group number. And we're already starting to see some reasonable responses in the chat. Don't be shy to share your responses, and I'd be happy to provide feedback. And we'll discuss this example in about another minute and a half. So the only thing that's new for abbreviated configurations is you take your long form electron configuration, you find the preceding noble gas, and you abbreviate your core electrons, your electrons with the smaller n values, the smaller number in front, using the noble gas. So for example, we abbreviated the 1s 2 electrons, these inner shell or core electrons, as helium. Does that clarify your question a little bit? Let's look at this example one more time. So boron, so the noble gas before boron is helium. Boron is also a group 3A element. Boron is in the third column of the periodic table. So boron naturally has 5 electrons, and its long form configuration would be 1s2, 2s2, 2p1. So just like before, we can abbreviate these core electrons using the configuration for helium. And that gives us helium 2s2, 2p1. Yeah, these abbreviated configurations really show their use when you're dealing with elements that have a large number of electrons. So once we've written out this abbreviated configuration, we just check and note that we have 3 electrons total. For beryllium, so looking at beryllium, again, our preceding noble gas is helium. Beryllium has 5 electrons total. So we take our configuration 1s2, 2s2, and we abbreviate our 1s electrons as helium. Do these examples make sense to everyone so far? If you know how to write basic electron configurations, then these abbreviated configurations are just a small extension off of that. So let's take a look at another set of examples, and I'll do the first one. So sodium. Sodium has 11 electrons to its name. Now I'm going to look in the periodic table here, and before sodium, what is the noble gas before?
Neon.
Yep, exactly right. Neon is the noble gas before sodium. So sodium has a configuration of 1s2, 2s2, 2p6, 3s1. Neon has a configuration of 1s2, 2s2, 2p6. So we're going to replace our inner shell electrons with just the symbol for neon. So that gives us an abbreviated configuration of neon 3s1. And as we see, we have 1 valence electron. Does this make sense to everyone? So let's take a moment and let's spend about 3 to 4 minutes writing the configuration for aluminum and chlorine. And we'll discuss this example in about 3 minutes. And don't be shy to share your responses in the chat, and I'd be happy to provide feedback. And let's try to get a few responses in the chat before we discuss in about another 2.5 to 3 minutes. And we're already starting to see a reasonable pool of responses. And we'll discuss this example in about another minute to a minute and a half. And don't be shy if you have any questions to ask them verbally or in the chat. Okay, so let's look at this example. So aluminum has 13 electrons to its name. It's a 3A element. And just like sodium, the preceding noble gas, I always like to draw a picture just to help me visualize what's going on, is neon. So aluminum's broader configuration is 1s2, 2s2, 2p6, 3s2, 3p1. We can abbreviate our inner shell electrons, and that gives us the configuration for aluminum of neon 3s2, 3p1. So it saves you a lot of time writing out the full configuration. Chlorine as well has a broader configuration of 1s2, 2s2, 2p6, 3s2, 3p5. It's a 7A element. We can abbreviate our inner shell electrons as neon, and then we write out our valence electrons as 3s2, 3p5. And notice when checking our work, our number of valence electrons always matches the group number. Does this make sense to everyone so far? Any questions on this idea? So we're going to continue on with this next class session.